All right, let's get into it. Ever wonder what's really going on inside all your gadgets? I mean, deep down, there's this hidden nervous system, a secret language that lets all the little parts talk to each other. It's called I2C, and you're about to see how this incredibly simple idea literally runs our modern world. Okay, just think about your phone for a second. Think about what's crammed in there. You've got gyroscopes, multiple cameras, light sensors, this beautiful screen, chips for managing the battery. It's just an insane amount of stuff in such a tiny package. Now, here's the kicker. The brain of the phone, the main chip, only has so many little connection points or pins to connect to everything. So how in the world does it talk to dozens of different components at once? And this right here, this is the fundamental headache for every hardware engineer out there. On one hand, we all want more features, right? More sensors, better displays, everything. But on the other hand, you've got this hard limit on connection pins. Every single pin is like a plot of priceless real estate. You can't just build more. It's this exact dilemma that forced someone to come up with a truly revolutionary solution. So, enter the hero of our story, I2C. This was cooked up way back in 1982 by Philips. You'd know them today as NXP. They looked at this growing problem and came up with a solution that was so elegant, so simple, it was almost hard to believe. They said, what if we could run pretty much everything with just 2 wires?
The name I2C just stands for Inner Integrated Circuit. And yeah, the official description is a synchronous half-duplex protocol. Let's break that down real quick. Synchronous just means everything is timed perfectly together by a shared clock signal. Think of it like a conductor leading an orchestra, making sure nobody misses a beat. And half-duplex? That just means data can travel both ways on the same line, but, not at the exact same time, one direction at a time.
And this is where the magic really happens. The entire system, dozens of devices potentially, runs on just 2 wires. You've got one for the data, that's SDA, and one for that clock, the conductor's baton, which is SCL. That's it. I mean, compare that to other protocols like SPI, which needs at least 4 wires, and you instantly get why this was such a game changer. It saves those precious pins, it cuts down on clutter, and it saves a ton of space on the circuit board. But okay, that immediately brings up a huge question, right? If you've got maybe a dozen different gadgets all hooked up to these same 2 wires, how do you keep them from all talking at once and turning the whole thing into just electronic noise? How do you avoid total chaos? I mean, think about it electrically. What happens if one chip tries to send a 1 by putting, say, 3.3 volts on the wire? And at the exact same moment, another chip tries to send a 0 by connecting that same wire to ground. Shouldn't that create a direct short circuit? Boom. You'd think it would just fry the chips, right? So why doesn't it?
Well, the answer is this incredibly clever electrical trick called open drain. And here's the one rule you have to remember. No device on an I2C bus is ever allowed to actively push the line high. It can't create a high voltage. Think of it like this. Every device has a little internal switch, but that switch only connects to one thing, ground. So all a device can do is pull the line low. It can't push it high.
So you're probably thinking, okay, if nothing can push the line high, then what does? And that's where this little guy comes in, the pull-up resistor. The best way to picture this is to imagine a spring. This spring is always there, connected between the wire and a power source, and its only job is to gently pull the wire up to a high state. That's the default. So when a device wants to send a 0, it just activates its switch and yanks that line down to ground, fighting the spring. And when it's done, it just lets go. And the spring pulls the wire right back up to high. And that one simple rule, you can only pull down, is the secret sauce that prevents all electrical chaos. Because think about it, if one device wants to send a 1, it just does nothing and lets the spring hold the line high. If another device wants to send a 0 at the same time, it actively pulls the line to ground. Is there a fight? Nope. The 0 just wins. The line goes low, and there's no damaging short circuit. It's an absolutely brilliant way to solve the problem. Now, this gets really interesting for the engineers designing this stuff. The strength of that spring, which is just the resistance value of the resistor, is a huge decision. If you use a low resistance, that's like a really stiff spring. It snaps the line back to high super fast, which means you can communicate faster. The downside? It takes more power to pull against a stiff spring. On the other hand, a high resistance is like a soft, gentle spring. It's slower, sure, but it's way more power efficient. And if you're designing something that runs on a tiny battery,
You can bet that trade-off between speed and battery life is something they obsess over.
Okay, so we've established the physical layer. We've basically built a perfectly safe two-lane highway where cars can't crash into each other. But now we need some traffic laws, right? We need a system to make sure the right data gets to the right place without causing a traffic jam, and that's where the protocol part of I2C really kicks in.
So in any I2C communication, you've got a few key players. First, there's always one master. This is the boss. It's the device that starts the conversation and controls the timing with that clock signal. All the other devices on the line are slaves. They just sit there and listen, waiting to be called on. We already know the SDA line is our data highway, and the SCL line is our traffic light setting the pace. And the most important part, every single slave device on that bus has its own unique 7-bit address. It's literally like a house number on a street.
All right, so here's how a full conversation goes down. First, the master gets everyone's attention by sending out a special start signal. Then it shouts out that 7-bit house number for the specific slave it wants to talk to. And it also adds a bit that says, hey, I want to write to you, or hey, I want to read from you. Now, out of all the slaves listening, only the one with that matching address responds. It pulls the line down for a split second to send back an acknowledge, or ACK. It's literally raising its hand and saying, yep, that's me, I'm here. After that, they can exchange data, always in 8-bit chunks, with an ACK after every single one, to make sure it was received correctly. And when it's all over, the master sends a stop signal and the highway is free for someone else to use. And through all of that, there is one golden rule that can never be broken. During a normal data transfer, the data on that SDA line is only allowed to change when the clock line is low. When that clock goes high, the data has to be held perfectly still, rock solid, so the other device can read it without any mistakes. This is why the start and stop signals are so unique. They're the only times the data line is allowed to change while the clock is high, which makes them completely unmistakable flags for we're starting or we're done.
Okay, so let's zoom out for a second. We've seen the nuts and bolts of how it works. But the big question is, why? Why has this protocol, something designed back in the 80s, which isn't even the fastest option out there, why is it still so completely dominant? Why is it the backbone of basically everything? First off, let's be fair, it has gotten faster over the years. It started at a pretty modest 100 kilobits per second, but now you've got modes that can go up to 5 megabits per second, so it's not a complete slouch. But, and this is a huge but, the entire bus, every device on it, has to run at the speed of the slowest device connected. It's like having a sports car stuck behind a tractor on a one-lane road. You could have a brand new, super fast processor that's forced to slow way, way down just to talk to a simple, older sensor. So even with that speed limitation, the reasons designers absolutely love I2C are just overwhelming. For one, it's simple. It saves those precious microcontroller pins. It's also incredibly flexible. Want to add another sensor to your design? Just tack it on to the 2 wires, no big deal. It's scalable. You can have over 100 devices on one bus. It's super robust because of that awesome open drain design we talked about. And maybe the best part for the companies making this stuff, it's cheap. There are no licensing fees, and it's dead simple to implement. So where is all this I2C stuff hiding? The answer is absolutely everywhere. Seriously. It's inside your PC, quietly checking temperature sensors and adjusting your fan speeds. It's the little network inside your smartphone that lets the main processor talk to the gyroscope, the light sensors, the battery chip, the whole shebang. It's in your smart home devices controlling the little displays. It's even in your car, managing a countless number of small sensors and modules. It is the silent, invisible workhorse of our entire digital world. And that really brings us to the final thought here. You have this solution that's now over 40 years old, based on just 2 simple wires and one incredibly clever idea, and it is still the foundation of so much of our modern tech. It really makes you wonder, doesn't it? What amazing new innovations in the future are still going to be built on top of this simple, elegant, and timeless 2-wire system?